Welcome. Today, we're diving into Boolean algebra and logic gates, the foundation of digital electronics. I'm A. Sindhu Devi from Jerusalem College of Engineering, and this is Unit 1. Together, we'll explore how simple true and false values power everything from computers to smartphones. Let's get started. Today, we're diving into the core building blocks of digital logic and computation. We'll start with number systems and arithmetic operations, then move into binary codes. From there, we explore Boolean algebra and logic gates, the foundation of digital circuits. We'll cover the properties of Boolean algebra, Boolean functions, and their canonical and standard forms. Then, we'll simplify these functions using Carnot maps before wrapping up with a detailed look at logic gates themselves. This sets the stage for understanding how digital systems think and work. Let's take a closer look at number systems, the way we represent numbers in digital computers. The most familiar is decimal, base 10, using digits 0 through 9. Then there's binary, base 2, which uses just 0 and 1. Octal, base 8, uses digits 0 to 7. And hexadecimal, base 16, combines numbers 0 to 9 with letters A through F. These systems are the foundation of how computers process and store information. Let's take a closer look at arithmetic operations in binary, the basic math that computers use every day. We've got four main types here: addition, subtraction, multiplication, and division. For example, adding 101 and 11 gives us 1,000. Subtracting 11 from 1010 results in 111. Multiplying 101 by 10 equals 1010. And dividing 1010 by 10 leaves us with 101. These operations might look simple, but they're the foundation of all computing calculations. Binary codes are the language of computers, strings of zeros and ones that stand for numbers, letters, and symbols. Each code has its own job. BCD, or binary coded decimal, represents decimal numbers. Gray code is designed to reduce errors during transitions. ASCII stands for characters, letting us handle text. And XS3 code finds its place in arithmetic circuits. Together, these codes form the foundation for digital communication and processing. Let's break down some basic operations in Boolean algebra, the foundation of digital logic. First, the AND operation outputs a 1 only when both inputs are 1. Next, the OR operation outputs a 1 if at least one input is 1. Finally, the NOT operation flips the input, turning a 1 into 0 or a 0 into 1. Boolean algebra works with just two values, 0 for false or off and 1 for true or on. It's simple but powerful. Let's talk about logic gates, the building blocks of digital circuits. These gates take one or more inputs and produce an output based on simple rules. An AND gate gives a 1 only when all inputs are 1. An OR gate gives a 1 if any input is 1. The NOT gate flips the input, turning 1 into 0, and vice versa. Then we have NAND and NOR, which are just the opposites of AND and OR. XOR outputs 1 when inputs differ, while XNOR gives 1 when they're the same. These gates form the foundation of all digital logic. Let's start by looking at the properties of Boolean algebra. These are the rules that guide how we work with logical expressions. They're essential because they help us simplify complex statements into something much easier to understand and use. Think of these laws as the foundation. They keep everything consistent and predictable when we're dealing with true or false values. Understanding these properties is the first step towards mastering logical reasoning in this context. Let's talk about Boolean functions, the building blocks of decision-making and computing. At their core, these functions take inputs that are either true or false and combine them using logical operations like AND, OR, and NOT. They help us create rules, solve problems, and control how systems behave. Understanding Boolean functions is key to grasping how computers process information and make choices. Let's take a closer look at canonical forms in Boolean algebra. A canonical form is a special kind of expression where every term includes all the variables exactly once. There are two main types, and the first one we'll focus on is the canonical sum of products, or SOP. This uses minterms product terms that cover every variable. The truth table here shows how the output relates to inputs A and B, helping us build these expressions systematically. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's break down the difference between canonical and standard forms in logic expressions. In canonical form, every variable shows up in each term, no exceptions. Standard form is more flexible. Terms might leave out some variables. When we talk about sum of products, or SOP, canonical uses minterms, while standard uses product terms. For product of sums, or POS, canonical relies on max terms, and standard uses sum terms. Canonical forms are great for representing truth tables exactly, but standard forms help us simplify logic more easily. Let's talk about simplifying Boolean functions using Carnot maps, or K-maps. This method helps us visualize and reduce complex logical expressions quickly. Instead of juggling algebraic equations, we arrange values in a grid, making patterns easier to spot. By grouping ones in the map, we find simpler expressions that do the same job. It's a powerful tool for cutting through complexity and designing cleaner, more efficient circuits. Let's take a closer look at how we organize variables A and B using a two-variable Carnot map, or K-map. This table helps us visualize all possible combinations of A and B, zeros and ones, in a simple grid. Each cell represents a unique pair of values, making it easier to spot patterns and simplify logic expressions. This approach is a foundational step in minimizing Boolean functions efficiently. Here, we're looking at a three-variable Carnot map, or K-map for short. It's a tool that helps us simplify Boolean expressions by organizing truth values in a grid. The variables A, B, and C are arranged so that only one variable changes between adjacent cells. This layout makes it easier to spot patterns and groupings, which means fewer terms and simpler logic circuits. It's a powerful way to visualize and minimize complex logic functions. Here, we have a four-variable Carnot map, or K-map, laid out as a table. The variables A and B label the rows, while C and D label the columns. Each cell represents a unique combination of these variables, making 16 cells in total. This map helps us visualize and simplify complex Boolean expressions by grouping adjacent ones. It's a powerful tool for reducing logic functions with four variables, making digital design more efficient and easier to manage. Carnot maps help us simplify Boolean expressions in a way that's more intuitive than traditional algebra. By minimizing the number of logic gates needed, they directly cut down hardware costs. This means circuits can be built faster and more efficiently. Overall, K-maps make the whole process of circuit design smoother and less error-prone, a real advantage when speed and cost matter. Here we see a simple truth table for a logic gate. It shows two inputs, A and B, and their resulting output, why when both inputs are 0, the output is 0. If either input is 1 but not both, the output stays 0. Only when both A and B are 1 does the output switch to 1. This is the classic behavior of an AND gate. It only activates when all conditions are met. Logic gates like this are the building blocks of digital circuits. Here, we're looking at two simple tables that show how different inputs relate to outputs. The first table lists combinations of A and B, and the resulting value Y. Notice how Y is 0 only when both A and B are 0. Otherwise, it's 1. The second table shows a different relationship between A and Y, where the output flips depending on the input. These tables help us understand basic logical operations, the building blocks for more complex decision-making. Here we have a simple truth table for a logic function. Notice how the output is 1 in every case, except when both inputs are 1. That's the hallmark of the NAND operation. It's a fundamental building block in digital circuits because it combines NOT and AND in one step. Understanding this table helps us see how complex logic can be built from just a few basic functions. Here, we see a simple truth table for the logical operation known as NOR. It shows all possible inputs for A and B, and the resulting output Y. Notice that Y is only true when both A and B are false. In every other case, Y is false. This table helps us understand how NOR acts like an inverted OR. It flips the usual logic on its head. It's a fundamental building block in digital circuits and logic design. Here, we see a simple truth table for a logical operation. When both inputs, A and B, are 0, the output Y is 0. But if either A or B is 1 and not both, the output flips to 1. Finally, when both inputs are 1, the output returns to 0. This pattern is the hallmark of the exclusive or XOR operation, a fundamental building block in digital logic and computing. Here we see a simple truth table for the logical operation known as XNOR, or equivalence. When both inputs, A and B, are the same, either both 0 or both 1, the output Y is 1. But if the inputs differ, the output is 0. This table helps us understand how this operation checks for equality between two binary values, a fundamental concept in logic and computing. Let's wrap up by revisiting some key points about Karnaugh maps. They're a graphical tool that helps us simplify Boolean expressions quickly. Gray code is used because only one bit changes between adjacent cells, making grouping easier. NAND and NOR are universal gates, meaning they can build any logic function. XOR differs from OR since it outputs 1 only when inputs differ. In a 4-variable K-map, the largest group covers all 16 cells. Simplifying Boolean functions helps us cut down on gates, cost, and complexity. These are important questions to keep in mind.
Thank you for watching. Please do like, share and subscribe my channel.